And you can start putting wires back in a box or taking wires out of the box.
Okay, boss.
All right. With that thing down low like that, we can see everybody's face. Edge of the table. You're all color balanced and everything?
Yes, sir.
All right, why don't we do a run through it one time? And, now, let's see, she's got the only mind. The other,
Can you pick her up? Because she's going to be the one, right?
yeah. Let's have her, because she's closest to your mic, ask the question.
Do they ask the question?
Yeah.
Okay.
You're going to raise your hand and ask the question.
Yes.
Yeah, why are we learning all this technical stuff?
What am I supposed to say? That's a good question. I have a few friends that might be able to help us out. Let's go. That'll be it, right?
That's about it, yeah. Well, we'll run through it a couple of times, make sure everybody feels comfortable with it.
Why you ask me that dumb question? You leave.
Everybody awake now?
This is Bebe Class 101. Let's get busy. This is my posse.
Bruce? Can we put that robot on the other end of the table? What I need to do, see, is be able to see their faces, and then hide them.
All right, let's
Get everybody in. Now what we'd like to do here is go from the country off to the stage. See, we're just kind of have things, not anybody talking right at the moment. You be running that thing, and you be making your noises. Okay?
It makes sense.
Well, okay, but I need you making some mouth noises, you know, like Bronx cheer and all that kind of stuff, whatever comes up. And you can be concentrating on that or on what T's doing here, either one of the two, when we first open up. Yawns don't count.
Come on, John, sing some Bon Jovi for us.
Steve,
You know an Elvis, huh?
get your class going.
Yeah, it is. Some rap, man, you know. Okay, class, let's get busy.
You study the text in there. Probably looking at what he's doing. Okay? Okay, guys, give me some action. We're doing something.
Just stay on.
Okay, guys, about time to wrap it up. Supposed to ask you a question.
Did you say question?
Huh?
You said you have any questions?
Oh, okay, my fault.
All right, start it over.
Early in the morning, see, I don't drink coffee, so it take me a while to wake up.
We can tell you, we're gonna make questions, start as you get. The last thing you do, if anybody got a question,
Yeah, okay. I got you.
okay?
All right.
Let's go.
Okay, guys, let's wrap it up. Does anybody have any questions? Yes, ma'am.
Yes, why are we learning all this technical stuff?
That's a good question. I have a few friends that might be able to help us out. Let's go take a look at them. Yeah.
Go ahead and go up on that thing. Make it do something. Okay, let's go back to what we were doing.
That's good. It's real
Well,
good.
we can shoot it that way too.
Yeah, leave it right around in there and do things with it.
All right, she's asking a question right now.
That's what Lauren did for a
Can you show Lauren how to run that thing for a minute? Let's shoot one with her trying, okay? And we'll see what happens. You got plenty of tape out
Oh,
tomorrow.
yeah, I'm rolling.
All right, let's go through the sequence again with the question. Get it from the top. Come show her. All right. You can reach over. Roll it. Okay.
Okay, I'm gonna need you guys to read chapter 3 and 4. And it's about time for us to wrap it up. Anybody got any questions? Yes, ma'am.
Yes, why are we learning all this technical stuff?
That's a good question. I have a few friends that might be able to help us out. Let's go meet.
Okay, you're out of the picture.
Okay, class, I need you to read chapters 3 and 4. I may have a pop quiz on it tomorrow. I think that about wraps it up. Anybody have any questions? Yes, ma'am.
Yes, why are we learning all this technical stuff?
That's a good question. I think I could show you better than tell you the answer. I have a few friends that will give you the definite answer. Let's go take a look at it. Okay, this way.
Don't do exactly like you would if you were a kid. Slide back, and do that, go up to the end. Let's try it again. Be only quite so long before we start hesitating.
Okay, well, let me know when y'all roll. See, I don't know. Just say I'm moving or something. Okay. Okay, we'll need you guys to study chapter 3 and 4 because we might have a pop quiz on it tomorrow. And let's wrap it up. Are there any more questions? Yes, ma'am.
Yes, why are we learning all this technical stuff?
That's a good question. I have a few friends that might be able to show you better than I can tell you. Why don't we go out to the courtyard? There's a van out there, and we'll take a trip and meet all these people, okay?
I'm just shooting, I might use it for film. You can get that light to read.
Brian, come on in.
Brian, get around here. Right in there is fine. Might show it running some, you know, and then operating on the controls and try to describe what you're doing. Okay? Ready, Marlon?
All right.
Would you say a few words so we can make sure we got you on the mic?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay? All right, then from now on, ignore it.
Okay.
You're on the far side.
I think you'll pick them up about here.
Good morning, Steve. Welcome, welcome, welcome. How y'all doing?
Fine.
I'd like to show you an operation we're performing. I'm making some parts for something we'll call a precision segmented reflector joint. And this is the whole setup, but I'm just only making individual parts for it. I'm using a lathe, a programmable lathe to do this operation. And right now I've turned part of it, and I'm now about to cut the slots on the side here. So what I'm going to do is close the door and start cutting some slots. What I'll do is show you what the whole function of this part. As we will remember those Lego sets when you were small, this is somewhat similar to that. What we can do is take joints off, put joints on, run out long rods, and then there are other joints that these rods are going to connect to and make the whole assembly that NASA is trying to make and take out into space. Just like the Lego set, the ideal thing to do is take the parts off and put them in the box, or the canister, as you remember the Lego set. Well, here, NASA is going to take these parts off, disassemble it, put it in the space shuttle, and then take it out into space and assemble the parts by using these quick detaching joints that I have become real proficient in operating. Ah, there's one. It's off. So they'll put on the joint, add on the long rods, or the long rods may be already on it, and then assemble our precision reflector, segment reflector. Oh, there goes another one. So the machine here is doing all the work, as you may be acquainted with. We're using computers to operate the machine. This is our control panel here, and I give all of my commands to the machine via this control. And basically what I'm doing now is just turning it on, having it do the work. We have various tools in the machine that are actually doing the cutting. Right now we're using a small end mill to cut the slots with. In fact, what we'll do is once it finishes cutting the side of it's going to cut right now, I'll cut the machine off and you can see the slot that's been cut. So that everybody can sort of step forward. In fact, let me do a little bit. This is sort of stage one of the slot. So it's cut it on this side. The chuck has spun around. This is what we call this big apparatus here, a chuck. It has spun around, and now it's about to cut the opposite side. The opposite side hasn't been cut yet. So we have one side cut, and we're going to do the opposite side. So we have, basically what we have one side is cut. It was on, the machine cut on this side, so it has spun around. Now it's going to cut this side, along with putting that little hole on both sides. So there we go again.
Do you ever experience difficulties programming?
Oh, yeah. In fact, what we do is we write the program, and then we run the machine away from the job. So basically what I would do is, after the program is written, we do a test run on it. And the tool is way out here somewhere, so it doesn't actually come in contact with the machine. Because the machine, if you give it any command, it'll do it. It doesn't care if the tool is right here. If you say go forward that way, it's going to go forward that way. And what's going to happen is it's going to run into something. So what you do is you run it way back away from what you're cutting. Run the whole program that way and try to work out the bugs. So yes, first time, very seldom everything is right. So it's almost like what it's like working on your car. You think you have it right, and bang, you don't have it right. So that's the problem we have here. You know, it's easy to put in wrong numbers or skip a number, forget a number to put in, and all of that, has to be right. So everything has to be right. And you have to have a way of testing it out. That's our way of testing it out. course, at the same time, the dimensions can be off. So one of the things I have to do is periodically check this. These are called veneer calibers. In fact, I can pull out a piece of your hair and measure it and tell you actually how thick that piece of hair is with these things here. So I have to check it from time to time, and all of those dimensions are on the drawing there we talked about earlier. So we have to go over and check all of the dimensions, make sure everything is right. Because the dimensions, some dimensions are critical because we're trying to fit this piece inside of here, as well as this other piece on the outside. So they all have to fit together. So if the dimensions are way off, they don't fit together. So what we do, we have to throw them in the trash can. So that's something I periodically do. Okay, the machine has stopped again. So what we have now, we have a slot on this side and a slot on the opposite side. Now the next operation it's going to do is cut this part here in there. And that, once again, we're using another end mill. It's going to do that operation. So it's going to cut a slot in here and cut a slot in there. In fact, what you see happen is the part that has the tools on it is called a parrot. So I'll turn the machine on, you see it spin around, it spins to that position, and it goes in and do what it's supposed to do. That's sort of a slow operation. So it goes in and start the mill in here, and this thing is going to turn like that and do all of that. So that big part, the turret, it stays still, and the chuck does the moving here. And it's going to do the cutting like it's supposed to. Now, one of the other problems I have is after cutting X number of pieces, the tool began to wear down, and that causes dimensions to be off. So we have to, so it's not a case I come in the morning, push the button, and everything goes right all day long. I have to do checking, I have to replace tools, and various little things like that. But normally the tools last for a while, especially we buy special tools that have a long life duration to them. And, plus, this is not a hard metal. This is just aluminum. If it was something like a hardened steel, we'd probably be wearing them out much faster. Plus, we got this little liquid running on there, and that helps to extend the life of the tool as well. They're all kind of little, I guess, tricks of the trade, you might say, that you learn over a period of time to work with things, make it last longer. So what I'll do right quick, like while y'all are looking on, is make sure I'm making good parts so that only the trash can will have chips and not parts in it. These are normally pretty accurate, I guess I'll refer to them as ballpark measuring devices. We do have other types that really can measure down to real close dimensions.
It's about we're filling an order of 1,000 or 1,200 a year, and it takes about 1,200 to build a large structure, and that's working 8 hours a day for the whole year. Here you can get a better look at it's cutting the ears now. Show them the ears.
Okay, it's gonna come around here and cut like that. And then it'll do one ear, and then it'll rotate the part around and cut the other one.
Have they seen any of the completed part?
We're ready to go, and it would be nice if you guys could arrange yourself so we can see your faces. Maybe from the other side over there.
I'd like to stand next to Brad, so can you pick up that on the microphone if I stand close enough to him?
Yeah, if you just get on the other side so I can see you.
Okay. Let me set some of this stuff down.
How are they going to hear me ask the question?
Have they seen a completed assembly yet?
No, not yet.
Want me to get that or?
Eventually, maybe we work our way over there.
All right, now, let's reverse it around a little bit.
Let me get over.
Tell me where you want me.
Let me stand there so you can talk and. So here's the microphone. This is kind of awkward.
Yeah, kind of. What do we do? Just same thing we just did?
Yeah.
Okay, guys. He's going to bring you up and everything. We've got different people. T's going to bring them from over there. Just walk up here, shake hands with you like you did over there, and then
Okay.
you guys can form back over here, all right?
What are they, a special group of kids or something? Oh man, now the machine lifts back up.
I know it's going to be that way the rest of the time. No, they're just 7th graders that. What they're trying to do is they're trying to emphasize the science and math, trying to get them encouraged in that so that they'll study that.
I thought maybe it was a special group of 7th graders or something. Or a group of
First
special.
name again?
Hank.
Oh, okay.
Hank.
Or a group of special 7th graders.
No, they just got picked to be in the film.
Single file, everybody.
Hello, how you doing? My name is Hank. I'm a technician out here, and they can hear us, so we better be careful. He's worse than I am. Morning. Hi, my name's Hank. This is Brad.
Hi.
We're technicians out here. We're presently making some space station parts on this 5-axis machine. Brad, you want to tell them what you're doing?
Okay. Y'all just came from the lathes, and lathes make these parts called blanks. They do one operation on it. Then we take and put them in the machine. We have two separate parts that this machine does the same operations on. I'll take and set one up in a fixture. The machine will take it in and cut it. Then after it gets done with that part, it'll remove the finished part, switch around, put my next blank in the machine and cut that one. It ends up cutting, interlocking grooves and ears on the pieces so that they can actually be locked together.
Let me get a working part here. Here's what a completed assembly looks like. So the part he's making now is this right here, the body, and then it's later on assembled here. And they'll lock them together like that. There you go. Anyway, y'all can play with those. So you're about ready to graduate from the apprentice school this year, is that correct?
I've been at NASA for approximately 5.5 years. Started as a co-op through Thomas Nelson, and upon completion of the mechanical engineering technology degree, they hired me on as a full-time apprentice. And in October, I'll have finished all my apprentice curriculum and be a journeyman machinist.
That's great. Class speaker too, huh? That's good.
Yeah.
What kind of science and math requirements do they have? Is it difficult?
It's challenging. Several physics courses, several math courses, and engineering courses. A lot of them are interrelated. Little trick to this, it's a lock. You got to pull back on it, spring loaded. Pull back on it. Oops, okay, there you go. already unlocked. There you go. Now you put it together.
Hey.
Now twist it a little bit more. It's not quite locked. With the astronauts with their bulky gloves and stuff, we had to make it a positive stop.
Eventually, well, right now we've built this, and then what that does is creates a parabolic shape, like an antenna receiver. And eventually they want to build this, and they'll build it out in space, and they'll just leave it there. And this piece I was telling you takes about 1,200 parts to build. It's a lot of work. Plus each one of these columns has to be within 1/10,000th of an inch
In the
of
overall
accuracy. That's correct.
What kind of information will you be getting back by doing these surveys?
They're mostly communication antennas, aren't they?
Right. This particular antenna is for, it's actually called a sub-millimeter astronomical laboratory. So it's like an infrared telescope in a sense. But basically our research is studying the strength of these structures and if they can withstand the temperatures and the vacuum of space. So it's still an experimental stage, but it takes lots of them to get the experiment to work. You want to explain a little bit about your machine? Or did you? You can't see it real well here. You want to?
Yeah. In a minute you'll be able to. When it comes down again, it's going to be finished.
That may be a good time.
I don't know all that much about it yet.
Kind of put him on the spot.
Put me on the spot there, Hank.
Where are all the women?
That's a good question. Out of about 80 employees, we have 12 women that are working. We're constantly getting more every day. They're all running machines. Right now, there's one, Mary's running the Cincinnati NC machine. Okay. Back on you.
Where are all the women?
That's a good question. In our machine shop, we have about 80 employees, and there's, I think, 12 women working here, and they're all over, working on machines and in the drawing section. But right now, Mary's over on the Cincinnati. We can go talk to her. Here's another wing. This is a wing with a built-in winglet that they're experimenting with. See, here's an example of starting with a solid blank. As we got you, always on the job. You all play with computers at work yet? I mean, at school?
Yeah.
When I first came here, I'd never dealt with a computer like that, a personal computer. And all of a sudden, they got a bunch of these in so that we could store programs on here instead of in the machine. If we had to buy a larger memory capacity for the machine, it would cost like 10 times the amount it would cost to buy one of these. and this holds 10 times more than that. So we got a few of these, and we were a little bit intimidated at first, but we use them all the time now. What we can do is we can bring programs down from upstairs. The programmers, the guys that write the programs for this, work up there. Used to be, they'd bring us down a punch tape, and we put it in a tape player down there. But now they've gone to, everything's by wire, like a telephone.
Do you have to memorize like lots of kind of signals and stuff to type in? Do you have to memorize?
It's not required that you memorize them, but if you don't, you should have them written down. But you just automatically memorize them because you use them so much.
Okay.
But what she's telling it there, see that T, comma, D1, and then, okay, what she's saying is run that program. She's calling up a program and then saying it can't find it. So that's a little code you got to remember, but you don't. There's hundreds of codes in here, different codes that's required to run the machine, but we're not required to memorize them because the machine knows them.
Oh, okay.
We just basically have to know how to call up the program. What do you want me to talk about with Mary? Just math and science?
Yeah, we're running short on time now. Is Mary going to be over here?
No, Mary's here.
Okay.
That other girl, you want her by that lathe too?
Well,
she's ready.
What I was thinking was we need to cut this, so we got to move on.
Okay. Let me go get her, and I'll leave this with Mary. Mary, why don't you just talk to him like you're talking to anybody else, and they'll just keep what they want, okay? That's what he wants to say, but I don't think it's... I gotta go get...
See my cooler now, okay? I'm trying to get the cooler on the tool so it won't ruin the cutter. This is about the hardest thing you have to do right here. Okay. Each one of these programs are separated to different programs. I guess you can see how each step in this, and they each have a different program. I just call up the upper circuit program for number 3, which is right here, which is the back side. They have a front side, which is a separate program also.
What is it doing now?
It's taking off 50,000 from this surface. This surface, all of these surfaces right here are finished. These surfaces here have 50,000 more to take off of metal. It's just one. Excuse me. And this tells you which program I'm running US 3. That's a section of the model. And operation is successful just tells you that you have the right program up. And we use this keyboard to write up here. The MDI is manual data input. And that's how we bring up the program to run this with. And we call up the programs from upstairs using the PC, and we bring everything from the PC over here to this computer to operate this machine. That's all it is.
Okay, it's time to leave. Thank you.
Okay, thank you.
Thank you.
guy wants to talk to you.
Can you hear? How do you want us to? Yeah.
Yeah.
Take this,
Give
Becky.
her the mic.
Good. Sorry about that.
Okay, I'm gonna
Just don't turn the machine on.
down here.
Why don't you stand behind her, and that way the people who are talking to them.
Yeah.
All right.
Yeah.
Put that fairly close to you. We got too much noise in here.
Is that good?
Yeah. All right. You know to show them with the mic so we can impress math and this kind of thing.
I'll try. I mean, should I explain to them that's the diameter and that's what
That's
I'm
a good
going to
idea.
be?
Yeah, and maybe show them the mic reading.
Okay. Okay. I'm remaking some pins for a sting that came out of the wind tunnel, and this is the diameter right here, 562.5 thousandths. So that's what I use these micrometers for, is to check the diameter. And you can see 500 is right there. And then each one of those lines is 25 thousandths. So that's 550 plus 62.5. And then you can even get down to tenths by reading this scale right here. But this is a pretty close tolerance pin, so it's kind of difficult to get that dimension.
Good to me.
Okay.
That's good. What did I do?
I'll start shaking. I hate stuff like this. Okay.
Thank you, Becky. You did real good. I think we might want to sign a contract. Is that going to be good enough?
Yeah, that's okay. We'll be cutting those others when we. As they come in, I'll try and get in here and get kind of tight on what you're doing, what you're shooting, or what you're working on there while you're explaining. Okay, and just go from there now. Pressure that over here. Yeah. Yeah.
Rolling.
Okay, roll 'em.
How you doing?
Hi.
Come around, class. This is Mr. Vince Cruz. He's going to tell you about microelectronics.
Okay, this is the microelectronics section of electronics. Right? So what we do here is we custom make electronics for different researchers and engineers in the field. What I'm working on right now is a real small circuit board. Have you all ever looked inside the back of a radio, television, or something like that and saw circuits, boards, and you see some things like this sticking off through these boards? What somebody did was they had an idea and they wanted us to make something for them. And what it was a little circuit board. They have to put these things on models. And this had to fit inside the model itself. This is one of the models that fit in. I've already made one, and I'm trying to make another one, a little bit smaller. They gave us some specifications they needed for it. They wanted it's it's real small. It had to be an inch in diameter, and it also had to be a quarter inch thick. And if you look at a standard circuit board, it's fairly large compared to an inch in diameter or a quarter inch thick. So we had to go to something a lot smaller. We had to get some specialized components, and we had to develop a few techniques to make the circuit. And what it and what we started out with just an idea. And one of the senior technicians I work with, he had to come up with a circuit that would do what they wanted to do. So he went through a few books, what they called data books, and he looked around for the components he would need to make this circuit. He had to use a lot of math, use a little bit of chemistry around here to do the things we could do. We had to figure out, calculate some of the currents and voltage. And with that, you have some pretty standard math equations you do. So he spent a while trying to figure out what he needed to do. And when he figured all that out, he started laying out the design. And as time went on, he'd get one design and he'd modify it more. He'd just keep changing it until he finally got what they wanted. And what he came up with was this circuit right here. And all these components he had to find and put together to make a circuit. So he got all his parts together. He gave a man over in packaging this schematic to work with. And the man over in packaging got on his computer, he started laying out the circuit board. What it is, it's just it's a path of electricity. Once you put all the components on there, you can hook it up. Electrical current would come in, do what it needed to do, and come out.
We'll get that just a minute.
Okay?
Go ahead.
You get it?
You'll get what?
That circuit.
Oh. Hello. Yes.
And after he was finished working with his computer, this is what he came out with. And this here is a part board. But what we start out with when we're making the circuit board is a gold-coated disc. And this circuit board here is exactly like this one here, but we needed to take all the extra gold off. So using chemicals and a few photo processes, what we did is from this and this, we went to this. And then after we put the made the circuit board, we had to start installing wires and the components. Now, a standard semiconductor chip, something like you see on a regular circuit board, is about this size. But in there, you'll find these little black squares. That's the heart of an integrated circuit. These little black squares right here with the silver on top. That's what an IC integrated circuit looks like when you take it out of its package. They make it this way so it'd be easier to handle and to solder on a standard board. So we made this, and then I started putting these together. What I had to do was more or less solder or glue down these components, and then we have this specialized machine that takes some very fine gold wire and it makes the electrical connections to it. With these wires, I'll hook up the signals, what they call signals going out. What this circuit board does is it takes an electrical signal, well, it takes electricity and it makes a signal. And this is what you see as a signal. It would turn off and on these little invisible light transmitters, and that's exactly what they wanted to do. And they wanted to do it at a certain rate, like off and on for maybe 1/1000th of a second. And he had 8 of these transmitters he wanted to do that with. So what it would do, it would sequence. It would go from one to another to another. And every time these things would turn on, they'd be on for 1/1000th of a second, which is pretty fast. You can't see the light in this transmitter, but as you see when I pull it away from here, what this does is this senses it. And so over in the packaging side of the department.
Hold it a minute.
Gotcha.
What? Have one of the kids ask. Something. I'm waiting for kids.
Okay. All right. We're gonna change a quick question here on you.
Okay.
Ask him, what are you
Sit
gonna do
forward.
what are you gonna do with this after you get it made? And we need to
Sit
be getting
forward, please.
closer.
Okay.
There you go.
Okay. Ready?
Yeah. What is all this
Wait a
for?
minute, wait a minute. Not, what is it, what are you gonna do with it after you get it made? What are we gonna use it for after you get it made? Okay, got it? Roll.
Yes.
What is this going to be used for after it's made?
Okay, once I finish putting this package together, it's going to go into this model. And they're going to put this model in a magnetic suspension tunnel. A magnetic suspension tunnel tends to levitate something. Okay, this looks like it's just sitting in the air like this. No strings attached, no wires. And they're going to be using these little transmitters to show how much this tunnel model moves. And so what they want to do is find out how the position is and in the model. So all these little black dots you see on this picture, those are transmitters. And they've developed a specialized camera to pick up this invisible light, and they've hooked it to a computer, and it's going to tell them how this model moves inside the tunnel. So that's what the whole thing is for.
Okay. I think we've got about all we can get out.
Yes, I am.
You ready? Okay, bring them in, T.
How you doing, Donnie?
All right.
Class, this is Donnie. He's going to tell you about printed circuit boards.
This is printed circuit board layout. This is called hand taping. This is something that we're trying to get away from now. We're trying to move up to computer layout of circuit boards. And what we start with is a schematic like this, which is just an electrical diagram of the way different components would be hooked up. And we actually look at this schematic and try to picture this in our minds as to where exactly these components will be placed on a circuit board. And all these tape lines on here represent the lines on here. These are some of the tools that we use. Scales. These are calipers for scaling things. Knife and tweezers for actually laying the tape down. Some of the tapes, some of these pads that we use to represent the holes that will be drilled into the board to accept the pieces, the electrical components on the circuit board. We also have data books to go by to learn about some of the components that we'll be putting on the board, as well as circuit requirements. We have specifications that we have to go by, rules to go by for placing our components on the boards. And as I say, this is a method that we're trying to get away from because it's time consuming, and as such it costs a lot of money, whereas with computers you can move a lot quicker and accomplish a lot more. This is a real small board. Computers can generate much larger boards than this in a lot less time.
Okay.
Any questions?
Do you have an honest question you'd like to ask about it?
Dishonest question.
Like, how would you put
Okay, what this?
that on the computer?
How would we do that on a computer? Well, are they going to go? Vicky, I thought you were Wayne Williams for a second.
Well,
You're taking them into computer layout, aren't you? That'll probably be the next phase that you go into, where somebody like this guy's got a computer, and basically what he does is you'll see it in another room. You'll see this actually on the screen, and they can type in different commands to the computer, and you can actually draw it on the screen. Whereas somebody that was doing this job actually has to take a piece of tape, lay it out, cut it with a knife, and so on and so forth. So, working with a computer is a lot easier. You just press a couple buttons and it does that for you.
Are these different wires color coded?
Yeah. Actually, this particular board would have two different sides to it. This would be one side, being the top side, and this would be the other side here. And on the computer, you'll see that since you're working in one dimension on the computer screen, you'll have different colors to represent the different sides of the boards to help you keep from getting confused, because that looks real confusing right there.
This is just the first stage of it.
Yeah, basically, after we get the schematic, it goes to this, and then this serves as a, we take that down to what we call the PC lab, the printed circuit lab, which is elsewhere on the base. I don't know if you've been over there, probably not, but, and they start with just a sheet of plastic which is coated on both sides with copper. And they use this as a mask, and using acid, trying to make the process short, and I'm trying to explain it in a short way. Using this as a mask, what they do is basically they shoot this image onto the sheet of copper, dip it in acid, and the acid etches away all the clear areas on here, and the copper, all these lines on here are left on there.
Okay.
Okay.
All right.
Thank you. Thank you.
Thanks, Tom.
Sure.
Short and sweet, I like it. Are you ready, Clarence?
Hang on.
Yes, I guess so.
I don't know if one of these ready or not.
Okay.
Okay, go.
How you doing, Clarence? Just fine, just fine. Well, Clarence is going to tell you about computer-aided design.
This is case software, and this represents a printed circuit board that I've been working on. It's essential that you have a strong math background in order to get these components in the form that you see them now. One of the advantages of computer-aided design is that you're able to pick components up and move them around easily. You're also able to remove lines that you don't need. You can also insert lines. Different sizes. Different lines moving around. So that makes our work quite a bit faster and easier. We can also reduce the display to let you see what the overall size of the printed circuit board would be. That's basically the advantage of computer-aided design.
Do you get your information of where to move it from the diagram?
That comes from experience of doing the layout. The information that we get comes from the engineer on our schematics, but it's up to the talent of the technician on how he wants to design for it and where he needs the placement of the components.
How long would it take you to make circuit on or design it on?
That depends on the size of the job. If it's a job very simple, it could be a matter of a few minutes. If it's a job very complex, it could be a week and a half.
What's the next stage after this?
The next stage will be to post-process this job. That means getting the information that we are showing you graphically on the machine to actually get it out on a physical PC board along with the proper documentation.
Okay, thanks a lot, Glenn. Have a good day.
Oh, you do the same?
Thank you.
Good job. Good job.
They did it last time.
Oh, I missed the last one.
I'm one of those people that
Some tunnels are called 7 by 10. That tells you that the air testing area is 7 foot by 10 foot. Others are like 22 inch. So you have to, the scale varies depending on which tunnel you're going in. And static models, the scale will vary too. Get them all answers out of them now.
Yeah, answer questions. Ask them questions. Are you rolling?
Yeah.
Oh.
Well, we got to bring them in, Marlene, first.
Well, we can always do that. And you
Did you make those things?
Back up,
Yeah.
bring 'em in.
Did?
uh-huh.
How?
The little models?
No. The hand with the clock in it?
Oh, no. That you can buy.
Oh.
Hey guys,
Oh.
Got it?
come walk over here and just walk into the seat. Come back to
This
where you
way?
were standing.
What is your
Remember where
name,
you were
sir?
standing?
Ben Gunther.
Don't call him Benji. Okay, I'm rolling.
How you doing, Mr. Gunther?
How you doing?
Class, Mr. Gunther's gonna tell you about how to make models.
Good afternoon. How you doing? Where shall we start? This is a 1/200 scale model of the space station Freedom, and it's, as you can tell, it's made out of brass that is soldered together. And we have one over here that is more assembled, and it's already been primed and painted. And what we're going to end up doing is painting the whole thing white. All right. So that's a little bit of a nutshell right now. Do you have any questions? I know you probably do.
Ask your same question.
They're all questioned out.
Well, what is the purpose of rebuilding them over and over again, but in different sizes?
Okay. As you can, the Space Station Freedom is a large structure, and this is the advanced version that have been the growth version. As you can tell by this size, it's manageable. You can put it on a desk, and you can see all the component parts. Now, if you had a larger scale, like 1/72nd scale, it would be on the order of 8 to 12 feet wide and about 6 foot tall, and that would be too much to put into an office for a conference, you know. So this is something you can take around the places and you can see. However, if you want to zero in on a particular area, like the upper boom here, you can do that in larger scale, and we did that over there with that particular model. And over there, that model that you see inside the boom is part of the Mars transfer vehicle. And that's the second part of President Bush's space initiative, where the first part would be returning to the moon and setting up a lunar base, and the second part would be landing a man on Mars, probably in the middle part of the 20th century. Of course, that has to be funded, but before they even start the funding, they need ideas and they need concepts, and these things, while they are good on computer or printout, they gain more realism when you can make a model of them. People immediately see and understand you seeing a model.
How long did it take to make that model?
All right, we've got 3 or 4 people working on this, but we had one man working particularly on the Mars return transfer vehicle, and it took him on the order of about a month doing that.
What is that right there in your hand?
This? Okay, well, like I said earlier, I'm going to get ready to sandblast this, so I took the modules off the space station because I didn't want to be in damage when it's sandblasted. But this is what it looks like. So right now you just have the basic skeleton of the space station. You don't have the solar panels or the dynamic electric generators on it or anything else, or you don't have the living and crew quarters and the laboratory modules. But that's basically what it looked like. And these things are on the order of 14 feet and about 30 feet. And you basically would have 4 of them. You would have the U.S. crew area, and then there would be the U.S. laboratory, and then the Japanese would have their own lab, and the European Space Agency is planning to have their own lab. And then these modules connect the other 4 together. Okay? And the idea is to be up here, and your space shuttle would come up, if my hand was a space shuttle, and would dock to the port here to resupply. Because they would have mobile arms hooked onto that would move around, and when the shuttle came in, this arm would come over and take whatever payload it had out, connect it to the space station for resupply, things like that. Okay, any other questions? And on the upper boom, you would have payload instrumentation that would look at up into the heavens. And on the lower boom, you would have other payloads that would be attached that would examine the Earth. So that's a scientific aspect, besides the labs that would do research in medicine and metallurgy, thin films, things like that.
Oh, so these are like cameras?
Well, it could be anything. I mean, right now, I know they're going to plan different observatories that the scientists in the labs could be studying real time. In other words, they could zoom into a particular area. The other satellites in orbit could take general broad views, and if they found something of interest, then they could come up and use these things to zoom into something particular. But the idea is the upper boom would be basically pointed away from Earth, so you look at the planets and the universe and things like that, whereas the lower boom would be oriented towards the Earth. So you could have cameras and other type of sensors down there and looking at the weather and ocean, different types of exploration that way.
How do you use math in order to make these models?
All right. Well, what we basically use is a lot of geometry and trig and some algebra. It depends. This particular model right here is what you call a display model, and basically we would have some geometry figuring out the structure. Where we use most of our math and everything would be when we start actually working some airplane models. Then you would have the different angles for your wings and your flaps, putting the different components together there. That's where you'd use most of it. So I would say you didn't need, geometry and trig and algebra.
How about science?
Science? Well, when you come out here in the apprentice program, not only will you get that math, but you also have other courses like strength of materials and physics. And while they don't have an immediate bearing, they're a good background, especially the strength of materials. I mean, it's something that you'll work into everything eventually.
On this, how do you know how to build it? Where to put all the pieces? Do you take it off of the big model, or do you have a diagram?
No, we have drawings, basically. Now, some of the models will be specifically spelled out, and they're very specific where they want things. Others are more general nature. They're quite specific about the initial part of the space station, which consists of an area about that far out and just a center keel. All right. The other part, the extensions and the upper and lower booms, are right now something that's being planned for maybe 10, 15 years after the initial space station goes up. So that they're still playing around with putting things as far as locations. That's one of the purpose of the models. They can move things around on the computers and they can print that out, but like I said, it gains more realism when they can actually start moving things around here and placing things. Sometimes you can see things three-dimensionally on a model that may be hidden two-dimensionally on a computer screen. Even if it rotates three-dimensionally, it may still be hidden. But that's something that you can spot immediately with a model.
Do you use computers to make drawings also?
We do. We have a section in the back room that we have some programmers. We have an NC machine, which is a numerical controlled milling machine that we can cut different, we can cut wood, metal, foam, parts for models. In fact, sometimes the whole model on it. And the people there use the computers, and they have the printout capacity if they want to. Now, this particular model it was generated, all the information was generated over Space Station office. And if I had a question, I would just call up to the researcher I'm working with. If I wanted more for clarification, he would just get that, bring it up on his computer screen and print it out and then send it to me. I don't actually have a station here tied into his network.
Okay. All right, thanks a lot.
No, all right.
Have a good day.
All right, thank you.
I'm just going to get a few close-up shots of some of this stuff that's happening.
And I think the gentleman wanted me to work in something about the spin models too. I remember him saying something about that.
We're not going to have time to put all that on the video, right?
Oh, doesn't matter.
Can you do a 5-minute blurb on spin models?
I can talk about it, and then you have to start going like this when I hit 5.
Yeah, let me get a few close-ups of this though first. I need a couple of those and a couple of that. Oh, it's still moving. Y'all get out of the background. Hello? Brian, just give you a double cheeseburger, okay? All right, 2 double cheeseburgers.
2 double cheeseburgers, wow. Kind of came at a dead time for us. We got some people in. We got 4 or 5 people in the NTF tunnel, and we got about 4 or 5 people in 16-foot tunnel, and we got another about 6 people stuck over on the other side, on the Langley side, doing some work on making fan blades, and we've got about 5 or 6 people working on a secret model back in another room. So by the time you can take about 3/4 of the shop out. It makes it look a little on the dead side.
You did a really nice job.
Okay.
I know.
Portable spill. Don't leave home without it. That's a 2-part epoxy. It's called Repro 83. And the nice thing about it is it has a fast gel time. It starts gelling up after about 10 minutes and goes through a consistency getting thicker and thicker, and after about 15-20 minutes it becomes solid. So while it's in that in-between stage, you can make some, if you got excess like we often do, you can make things like that with novelty items. We use that for making molds and for making component parts. We make our own rubber molds, and then we basically, doesn't matter what scale you do, you can start with the original pattern and then set this down, surround it, you can then pour rubber around it, and then you have a mold. Then you can in turn take some of this material, pour it in here, then pop it loose and make numerous castings.
That's how they do it.
Yeah, now the sizes can vary all up and down.
They were asking about those pieces over there, if y'all ordered those.
Well, no, you just make them. But that way you only have to make one, and then you just keep casting multiple pieces depending on how many you need. There's so many different techniques you can use in here. That's one of the things you do in the apprentice.
I'm sorry.
That's one of the things you do in the apprentice school. See, I'll have a couple people working under me, and I have certain ways of doing it, so they'll learn that. And then after a while, they'll go to someone else, and they'll learn. By the time they finish, they keep going around to different people, and they should have a good idea, a little bit of everything.
Right.
And then it's just a matter when they start doing it themselves, what they feel comfortable with. Into like a peanut butter consistency, it keeps getting harder and harder. until after about 20 minutes it's hard. Well,
Can you pick it up?
oh yeah, but what I mean is you can pour it just, if you catch it just in the right stage, you can start making novelty items like that. Those are just, leftover pieces, leftover, huh?
Wouldn't it stick?
Well, you have to put down a release agent, let's say.
You ready to go talk about the spin morning?
All right, then we're going to show you and talk about some aircraft models here. Now, this is a cutaway of a spin model, but this is actually the same thing, but this is actually the spin model. Now, one of the worst things that you can have in aviation is if your aircraft goes into a spin, specifically a flat spin, where the aircraft is rotating flat, rotating like this. It's very hard. Well, the pilot has no control, basically. And unless he knows how to get that aircraft out of it, he's going to end up having to eject, and they'll lose that aircraft. So nowadays, experimental aircraft are extremely expensive. So it's easier to make a model of that and test it to try to find out the different control motions needed to get you out of a spin. Now,
Walk on the other side. He's tall. You get right up front. He's tall.
okay, the Langley's is lucky in the sense that they're one of the only 3 locations in the world that has a spin model. One's at Langley, one is in France, and the other one is in the Soviet Union. Okay, so, and the spin model, the spin tunnel, I should say, has been in existence since 1936. It was rebuilt in 1940, and that has been in continual use for 50 years now, that same tunnel. And the tunnel, you have a large fan at the bottom, and it blows the air vertically, and it exhausts up top, and you have about 3 floors. About the 2nd floor, you have plexiglass windows around the tunnel, and one technician will open one of those windows, take the model out, and throw it in like a frisbee, inducing a flat spin, okay? Because you want to put the model in a flat spin. And what you have inside the model are a radio control system. There's a receiver and a servo and the batteries, and you'll have preset controls at a certain angle. And once you get the model in a spin, the researcher will hit a button, the radio wave will go, it will receive it, and it will trigger a response, and the controls will move in an opposite direction. If you do this several hundred times, you'll eventually figure out the proper sequence to get an airplane out of a spin. And with that information, they go back and tell the Air Force or whoever the agency is that sponsored the model how you get that particular airplane out of a spin. So that saves, could possibly save a pilot life doing that, and also an expensive piece of aeronautical equipment.
How many wind tunnels do you have?
How many wind tunnels at NASA? Langley? Well, NASA altogether. Ames is another research center on the California coast that almost duplicates Langley. I think Langley has in the order of, it's over 30 wind tunnels. I know that. They're varying sizes. Some complexes will have up to 7 or 8 wind tunnels in one building. Naturally, when you go through Langley, you'll see the larger wind tunnels, but a lot of the buildings will have smaller wind tunnels inside of them. In fact, some of the wind tunnels can be as small as this surface table, just about 8 foot long. But that's usually for low speed, studies.
What's the high speed?
High speed? Yeah. Oh, I know they'll go all the way up to Mach 20. That's very fast.
Okay, thanks a lot.
Thank you. Okay, kids.
Thank you.
Right.
Am I out of your picture?
Yeah, you are.
Okay. Hold it.
Give me a mic up there. Say who you were.
Hello, hello, testing, testing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, guys. This gentleman's going to be briefing you. You can ask him a question or two. Whatever.
Okay, well, let me give you a little introduction of what we do here. These are called solenoids, and they are used in anti-lock braking systems in automobiles. And there are two different types of solenoids that are made here, and they're all used in the same system. You probably saw a assembly of them when you came in here. These little hoppers here, parts are put into these hoppers, and as the assembly goes by, these parts are fed by way of the robots onto the assembly. And the assemblies move down, they go all the way down through the end of the line, and then they are tested to make sure that they work properly down at the end of the line. You can see that there's different kinds of parts. There's steel parts like this. There's little rubber O-rings like this. There's also filters. You can see there are tiny little pins used in this part. And all these parts are produced over on the other side of the building, and we'll take you over there later on. Do you have any questions? Where is math used in this? Well, we have to keep track of the number of parts that come into this room and the number of parts that are consumed and go through the bowl feeder and the number of finished assemblies that are gone out. And we have to keep track of those parts because each parts are very expensive. And we have to know exactly how many parts come in. So as these parts come in, they are counted on these machines, and the operators keep track of the number of parts that go through. Okay? There's also different measurements that are taken on these machines, and we have to have some understanding of math to understand how these machines calculate their measurements. Okay?
How does this relate to science?
Well, you have to know a little bit about how hydraulics work. Hydraulics is very important in electronics. These robots work by hydraulics and pneumatics. Pneumatics is air actuated, and they operate by air pressure. And hydraulics is fluid actuated, operates by fluid pressure. And the science of physics and the science of airflow, which is studied in physics, is where you would learn about that. Also, these robots right here are operated by electronics and by computers. So computer science is very important to understand how these robots work.
Which company would use these? Which car company or whatever?
Which car company? These are used in Chrysler automobiles. Okay? And it's an option. It's an expensive option that's put on cars that people pay extra money for.
Do you get these for all different kinds of cars, or just one specific kind of cars?
They're used for the top of the line cars, you know, the very expensive cars. And it's an option that's available in very expensive cars.
How many have you done in about a day?
Okay. In one day, the goal is to do at least 1,000 a day. 1,000 a day. But we've operated this room up to 3,500 a day. 3,500 finished solenoids a day. So that means we have to have 3,500 of each of the individual parts ready to go for this line every day.
How many do you have about a month?
Well, there'll be the work days in this month is about 25 work days because we started early in the towards the end of July. So there would be 25 work days. So it would be 25 work days times 1,000. Okay, so that would be, what would that be? 25,000 for the whole month. How many what?
like stages?
Different stages? Well, this is what's called a continuous assembly line. These parts are assembled one by one, and it's finished at the end. So really there's two stages to this room. There's the assembly stage and then there's a test stage, where these parts have to actually go through a machine and the brake fluid is pushed through and simulated just like it would be in an automobile to make sure that it works correctly. So there's two different stages in the room. There's the assembly stage and then there's a test stage. Okay?
About how many individual little places would have to, or individual parts would have to be put onto the car?
Okay.
Like different, like that's one and that's one and that one. How many of those would have to go through in the assembly stage?
In the assembly stage, I think there's about 30 different parts. 30 different parts in here. Some of the parts are purchased parts, which means that we buy them from somebody outside the plant, and some of the parts are made inside the plant. We actually manufacture inside the plant, and we'll be showing you that later on. This part here, for example, is made inside this facility. But this part here is purchased. Okay?
The two lines are the same thing, like that end is the beginning and that's the end?
Right.
Just to make it go faster?
Right. It just stays and it's assembled one by one. So as you move down the line, there's more value added to the part. Okay? There's more parts added to it. See, to answer your question about science, this is an air cylinder right here. And that's used the air inside that cylinder is pressurized. And it pushes down to apply this part to the assembly. And you can see the air pressure gauge there.
How much air is in there?
Right now there's no pressure on there, but it can go up to 350 pounds per square inch. I'm sorry, that's 350 bars, 5,000 pounds per square inch. It's a lot of pressure.
About how many people would be employed by this line?
I think about 15 people. No, I think it's a little less than that. I think about 12 people. The reason why it's so small is because there's so many robotics used in it. It's pretty much all automatic. The people are just used to make sure that parts get into the bowl, and anytime there's problems with the machine, they're there to fix it. Like right now, they're over there working on a problem with the machine.
Did you have to have a college education to get like a job in the assembly?
You have to have at least a high school education, at least.
And what kind of special training would you need if you didn't have a college education?
If you had,
if you didn't have a college education, what kind of special training would you have to go through? Would it be here or at a special school?
She's cutting this off. Okay, where we're going to go next now is we're going to go to the measurements lab. The measurements lab is the place where they test these small parts to make sure that they meet all the specifications to go into the assembly. So that's where we're going to go next, okay?
Is that focus?
And what do you... Yeah, is the camera on? I'll save my question.
You can introduce them and then let her, we'll stop.
Are they picking everything up off this mic? This must be a sensitive mic.
Pretty sensitive. Go ahead.
Okay, this is the measurements lab. Tom. Okay, this is the measurements lab where the parts that are made across the hall here in the machining room are brought over here and they're measured for accuracy and tested to make sure that they meet specifications for the assembly area like the one we were just at. And Barbara here is looking at a part through a microscopic machine, and she's going to explain to you a little bit how it works.
Well, this machine could either measure parts in metric or English just by touching the button. And we can measure ODs, lengths, and also inside a part we have reflection. check a length. If you're working with a blueprint, you would line it up, zero it, bring to a specified line that would be on the drawing, and then you would get that length, which this is 4 millimeters, 980 microns. It checks angles, and it also has a computer, which when we're checking something that you have to level, you would take these two sides. If I was checking two sides over here and they weren't level, press the skew. It's called skew, and you'd enter one side. Bring it back down to where the other side is, and press that, and it levels it out. And then you're able to take another length. So therefore you get an average.
Any questions?
And what do you determine by doing these measurements? Just
What you do?
What we do is we have a layout that we work by, and we determine whether or not the parts are acceptable.
There's a
tolerance.
There's a blueprint. There's a blueprint, and that was made up by engineers, and these parts have to be made according to that blueprint. And this machine measures the parts to make sure that all the dimensions on that part are exactly right, within tolerance.
How much can you magnify it? Like, how much you can magnify it? Like, it's...
How much is this magnified?
Yeah, the highest.
That's 100 times.
Right now it's on 20.
100 times is maximum.
Go back down to 10.
How much would this machine cost?
This machine here, I don't know. Several $1,000s though, I'm sure. Any other questions? No? You can see that you have to have a knowledge of geometry to understand the different parts. When she was looking at the, she said the word OD. Does anybody know what that means? OD? It means outside diameter, which means the outside diameter of that part. So you'd have to have a knowledge of geometry to know what the diameter is. Okay, so there's the...
Do you need a knowledge of science
also? You would need a knowledge of science to understand this machine as far as the light, the magnification, and the light going through the machine. You'd probably need to know a little bit about electronics and computers, too, to operate this machine. So you'd need both math and science. Okay, any other questions? Okay, thank you, Barbara.
Thank you.
Tell us where we're going next.
Where are we? Why don't we cut for a minute and decide?
All right, lathe.
Yeah.
Okay. That would be fine, except we just shot about 3 hours of that this morning out of NASA.
Oh.
And, you know, quite honestly, when you're inside on the machine, you can't tell where it is.
You can't tell where what is?
The machine.
Oh.
Whether it's in NASA or whether it's here.
Oh.
I can fill that in.
Okay.
Yeah, I don't mean to appreciate what you're offering.
Well, I just don't know anything about the area that we're going to.
Okay, so one area that the last time we were here was over in Chester. Last one we wound up with a little stall.
In that plant place, they said it was...
Also one other measurement lab where you can go right down on the other side of the hall.
Where's Fred?
It's I don't even know what the name of it is. Technician's lab.
Sorry about that.
I mean, I can get us there, but
Just follow me, we're going down the hall.
name-wise, I don't have a name.
Okay, all you got to do is say, okay, guys, follow me.
Follow me, we're going to another
Just
laboratory.
say, okay, follow me, and that's it. Take off, like you're going out.
Okay, guys, follow me, we're going to another laboratory. What is the name of this lab?
It's a silicon test lab.
Silicon test lab.
Okay.
Test lab.
Stay there, y'all.
John can't see what's going on.
Up over.
Come around, look over Lori's head.
Okay, I'm going to introduce you, then I'll hand you the microphone, all right? You can explain what this is. Microprocessor test lab.
Silicon sensor.
Go ahead and speak a little bit so I can do
Silicon sensor test lab.
Speak.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is the silicon sensor test lab where we test silicon wafers used in computers and sensors. And Mark is going to explain what this machine is right here.
Okay, this is a micromanipulator wafer tester, and we have a silicon wafers 4 inches in diameter, and this particular one has 860 some chips on it. And these are accelerometers used for crash, for airbags in cars. And we have these probes here that will probe the electrical characteristics of each die.
This is actually just a very fancy microscope, right?
Right, something like that. And a meter, multimeter, voltmeter.
Y'all have any questions?
What are these? Are these the chips we were talking about? What are those? Hello? They're just there.
This right here is just a closer.
This is a hood that closes it to keep outside interference like noise and things out of it from entering into the measurements.
That says micro zoom. How far can it zoom?
I'm not really sure. It usually tells on these. This is 2 1/4. It's really hard to see them. We have one that's 8 times and one that's 25 times.
All right. Do you need a science education or a math education to know how to use one of these things?
And just to use this, now you probably really don't. You would need a science education to learn how to operate the equipment, the test equipment, the multimeters, the capacitance meters to do the plots of the capacitance versus voltage.
What are these little knobs here for?
This is called a chuck, and these adjust the chuck. These knobs will adjust it to go up and down, or on a z-axis, an x-axis, or a y-axis.
Is this difficult for some machinery to work?
No, not really. It's fairly simple once you get the hang of it.
What are these little, like, the sort of really interlocking parts there? What are they for?
All these here?
Those and the ones behind them.
So these are called BNC connectors, and those are for the cables that will. If you use this test equipment to test this wafer, then you have a cable running from here to the outside of this, and from the inside to here, that will run to these probes. That way you can close this if you need to get away from the noise that would be associated with it.
Are the wafers the only thing that you can magnify in there, or are there other
Well,
things?
you could probably put about anything in there and magnify what you want, but basically what this is used for is just for wafers.
How much money would this be? I mean, how much?
This costs $20,000.
$20,000.
What is that little, it's like a little mix with a wire around
Okay,
it?
this right here?
Yes.
Okay, these are the probes. What you would do would be to set this up, and then you use these to adjust the X, Y, and Z of these probes. And if we could look through the microscope, maybe we could look through there and see. You could see real good what each die consists of, and there are pads on there, probe pads.
And these probes will make a connection to these pads that would measure the resistance or the capacitance or whatever you're trying to measure in these parts.
So you would have to have some understanding of electronics.
Oh, yes.
You'd have to have some understanding of geometry to understand the microscope. You'd have to have some science, computer science background to understand the computer.
Right.
So math, science, computer science, you'd have to have all of those to be able to operate this machine.
Right, you would.
There's like a gear shift right there. It looks like a gear shift. It's right there. What is that for?
Look at there's a table here up and down.
Oh.
So that moves the probes up and down to different heights.
I'd like to look in there myself. See what that looks like.
With adjustive focus.
Where's that? Right here? Or is that the gross? That's the fine.
Okay, there's one big one back here. Is the, you might even need to change the zoom lenses. What you do is spin that around to where it blackens out. Get better resolution.
Nah, not getting anything. That's it, right?
Thank you. Thank you.
Thanks, Mark. Okay, where are we going now? Oh, automotive tests. Okay.
Is there anything on there?
Let me see if I can.
Okay, we're going to move over to the automotive test cells where we actually test the automobiles, and some of this equipment is tested on the automobiles. So let's go ahead and take a walk over there. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is the laboratory where this happens to be a Chrysler automobile, which we make fuel systems for. And what we do is we bring the cars in here and we test the engines inside the cars to make sure that the fuel systems are operating properly. We also do a lot of research to determine, come up with new ideas and better fuel systems for these cars. All this equipment that you see around here are sensors and computers that measure exhaust emissions and fuel flow through the engine and combustion in the engine. And that's what all these sensors and printouts are for. Are there any questions? I'm not sure. I'm not sure what that's for. It looks like everything is shut down right now. They're probably in the middle of an experiment and they've just shut down everything.
What does this do? The graph?
Okay. This is a printout that tests, you can see up here, it has water temperature, RPM of the engine, O2. Anybody know what O2 means? Oxygen, that's right. I'm not sure what these other ones are. They look like it's very hard to read the numbers on there. It measures all the different aspects of the engine. There's a tube back here, a sensor that comes out the exhaust that tests the different gases that come out of the exhaust. And it's very important when for car manufacturers today to control the emissions that come out of an engine. And what we do is we try to make fuel systems to make the engines run more efficiently. Okay, what this is we were able to bring the car in and put it down into this little well here. And you see those two big drums? This is a front-wheel drive car. So when we start up the car, we could actually run the engine and put it into gear and turn the wheels. Okay, and actually put stress on the engine. And what this does is that you can apply stress to either one of these, to these drums down here, and it will simulate being on the highway. Okay? Any other questions? As you can see, there's a real, this is very intensely integrated with computers, all of this testing. So a real good knowledge of how computers work. Again, you have hydraulics and pneumatics. You have chemistry that you have to know about to understand the emissions coming out of the exhaust. So a knowledge of science to understand chemistry and computer science is very important to be able to work in research like this. Okay, we're going to go on to the next area now.
Oh, I'm sorry. I was listening to you, but...
Check it down one.
Oh, no.
You got a seat.
And afterwards, you know who Julia Child is? The chef?
Just leave it. Nobody knows who knows that.
Dressed up as her and physically into her. And Curtis Finger kept on leading.
Okay, this is the actuator lab. This is where all of the injectors that we make are tested. What we're trying to test for here is to see what is the minimum amount of voltage that a injector will open at, so that when an injector is in a car in cold weather, the battery doesn't put out as much electricity. So we're testing to see how much electricity it will take to start to open up an injector. Ross here is going to explain a little bit how this machine works.
Okay. Well, basically what we have is we run our fuel injectors inside this boom room here, which is, we call it a boom room because it's sealed off in case there's an explosion. We're running very close to gasoline-like substances through the injectors. And in case there is a spark or something and there is something ignites, we won't get blown up. But essentially what we're doing is, like Pete said, we're measuring the minimum operating voltage, what we call the minimum operating voltage of the injector. And that is the lowest voltage which you apply to the fuel injector in which it will open and deliver fuel to the car so that the car can start. And a fuel injector, if you've seen through the manufacturing of the injector yet, I'm not sure if you've been there, but it's just an electromagnetic coil, which is either copper or brass wire wrapped around a pole piece, which creates a magnetic field which pulls back an armature or a moving needle, and once it opens, fuel is delivered to the cylinder of an automobile, and when that pulse is taken off, the injector closes and the gasoline is not allowed to go to the cylinder. Essentially, by doing this test, we determine what is the minimum amount of current which we put through that coil, which will still open the injector. Again, like on cold mornings, a battery is not as efficient as it is on a day like today where it's 80, 90 degrees out. When it is cold, the battery put out less voltage, and we have to make sure that our injector will still work in that environment. So what this is this is just a test to determine it. Now there's many tests that can be done with this stand. This is just one of them. Another test that we do is we will run just basically what we call baseline data on each of these injectors, which we will determine what's known as the dynamic flow and the static flow from the injector, which determines the injector calibration, how well it will work in the vehicle, because each car uses a different calibration of injector. What we do here is not every injector that comes out of the plant is tested here. This is pretty much an engineering lab which is done for either samples or for development work, where we're trying to determine the benefits of a change that we might be making to the injector. So what Joni here does essentially is she works on the computer here, and it has a lot of canned programs, or programs that are already like a already store-bought, if you will, like a Lotus 123. But we also have special programs for this for the work that we do as well, that are just basic programs, which are basic computer language. And like all this is just written in BASIC. It's not a canned program. It's a very crude language for computers, but it's also very easy to learn. Joni knows how to get into some of the files and change them herself, as well as just hop through the canned part of the program, because sometimes there'll be a glitch or something like that in the program.
You all have any questions?
Do you have a test for heat to see whether the injector, is there a certain temperature that it might stop working or something?
Right. We have some equipment over there that we're just developing, which is a test cell which will test the injectors, not only test the flow rates like they do here, baseline flow rates here when it gets hot or cold for that matter, but as well as doing durability testing in those environments. So if you're out running 500 miles a day in Arizona where it's 110 degrees out and you just run over and over, underhood temperatures can get up to 300 degrees Fahrenheit, or even higher now with turbochargers and superchargers and all that, low hood lines. So what we like to do, what we are setting up is a test to run durability and flow measurements in that. Right now, we don't do that. The hot is it's a very difficult test to do because of the fuel. As you know, fuel gets much more reactive when it gets hotter. The cold part of the test isn't that difficult, except for things freezing up on you. But the hot part, you have to be very careful in your handling of the fuel, or else you can use the boom rooms, and you don't want to use them. We've never had an accident here to date, but we are very cautious in doing it. And these rooms are very, very sturdy. But that is a good one. That is a good question, because a car barely operates at 68 degrees here, Fahrenheit, like we usually do. It hardly ever does. The underhood engine's always hot, so the injector's always hotter than really here. But we do some testing.
Okay. Thank you, Rob.
Surely.
Let's go on to the next area now.
Thanks, Rob.
Yeah. Go ahead. Go ahead.
How you doing?
Hi, I'm Pete Mara. Welcome to Siemens Automotive Electronics.
He's going to give you a tour of the plant, so I'll leave him in your hands.
Come on. Oh, watch the wire.
I know those sneakers are getting tired, folks. So try and get them up over the wire, okay?
Doing?
Hello, I'm Pete Mara. Welcome to Siemens Automotive Electronics.
He's going to give you a tour of the plant. They're in your hands.
Watch the wire. Good job, guys.